Okay, we're going to do 11.4, the normal distribution. I'm not sure why that didn't show up in my course outline, but it is a part of the class. For some reason, I must have gotten section numbers wrong. But we are going to do 11.4. So we're going to talk about a normal distribution of data here. What that basically means is very simple, is that a lot of data in the real world has kind of this normal distribution, meaning, or something close to the normal distribution, meaning if you look at, this is the height of men with different sample sizes of 100, and then we keep increasing the sample size for the whole population of the Earth, roughly. And it makes sense, right? There's going to be very few people that are really tall and very few people that are really short, and most people are going to be near the average. A lot of data comes out this way in a distribution. For example, test scores would be like this. The C is the most common score, and then there's not many A's and there's not that many F's. Okay, so this is a normal distribution is a curve that often illustrates data. Okay, sometimes it's called the bell curve. Other terms that you're going to see is bell curve, or the Gaussian distribution. These are all terms that are used for this shape of a curve as it relates to data. Okay? So we're going to talk about how we orient a bell curve in the distribution. So, and how we define something called z-scores. So we're going to talk about all that stuff here now. So the normal distribution is a model that we use to model data, okay? And it's used to make predictions about an entire population using data from a sample. So to build this theory, a couple things you need to recognize. In the normal distribution, the mean, median, and mode are all at the middle of the curve right there. So whatever that particular item is would be the middle. So the mean, median, mode are all the same in the normal distribution, and they're at the peak of the curve. It'd be the data value at the peak of the curve. Okay, so this is something we're going to talk about here, the 68, 95, 99.7 rule for the normal distribution. Okay, so here's the idea. These, you have your frequency, the number of persons or things that this data is true about. And then you have what's called, each one of these is one standard deviation. Okay, so basically the way the normal distribution works, okay, is that 95% of the data items, this is number 2 here, 95% of the data items fall within 2 standard deviations of the mean. So what that means is that 95% of the people or objects fall within 2 standard deviations of the mean. The average is right here, okay? So basically, if you're, this is something that we talked about before, if you're looking at blood pressure, for example, if there was an average blood pressure of 120 over 80, 95% of the people are going to fit within 2 standard deviations of that, okay, of that central figure, or mean average value. And approximately 99.7% of the data falls within 3 standard deviations right here. Okay, 3 standard deviations. So you can go 3 this way or 3 that way, above or below. So almost the whole population sits within 3 standard deviations of the average, okay? And then the 68% of the data fits in 1 standard deviation away. Okay, so we're going to use this information to start making some calculations and to start playing around with this and trying to interpret how this might apply to situations. Okay, let's take a look at a problem here. Checkpoint 2. Use the distribution of male adult heights in North America in figure 12.2, which is right there. Okay, that's 12.2. To find the percentage of men with heights between 62 and 78 inches. Well, the percentage of men with heights between 62 and 78 inches. Well, between 62 and 78 inches, we're just reading the chart, it looks like we're at 95% of men are between those categories. We're using that 68, 95, 99.7 rule. So for part A, really simple, it'd be 95%. Okay. Between 70 and 78 inches. So 70 and 78 inches. Well, if I go up here, it looks like this, whoops, hang on, looks like this whole distance here, I don't know why it's doing this to me, it won't let me. It looks like this whole distance here is 95. And so this black part here is half of that, isn't it? So what's half of 95? Well, that's 47.5%. Now above 74 inches, that one's a little bit weird. Let's erase some stuff here. Above 74. So that's this way, right? Well, let's figure out what's there. Well, if it's above 74, so a way to think about that is that this range right here is 68, right? Okay, this range is 68. So we know that this little wing right here that I just made and this little other wing have to add up. All three of those have to add up to 100. Agreed? Okay, so if I take 100 minus 68, I get 32%. And these two wings have to both add up to 32%. But both of them are equal, right? They're both an equal part of the distribution because this distribution is symmetric on the right and left. So that means it's going to be half of 32, which is 16%. Okay, so you have to do a little bit of geometry here to figure out how these percentages add up. Okay, so I just basically took out the 68 right here, and then I divided these two into 2. Okay, so now we're going to talk about something called a z-score. So a z-score helps us to pinpoint more precisely where we sit on this distribution. So z-score describes how many standard deviations a data item in a normal distribution lies above or below the mean. So the way we find the z-score is this formula right here. We take the data item, so maybe it's a test score, minus the average and divide it by whatever the standard deviation is, and it tells you how many standard deviations you are away. So if you're 2.5 standard deviations away, it would tell you that. So let's take a look here. The length of a horse pregnancies from conception to birth is normally distributed with a mean of 336 days and a standard deviation of 3. Find the z-score for a horse pregnancy of 342. So for part A, the z for 342, okay, we put a little subscript there, is equal to data item, which is 342, minus the mean, which is 336, they give us in the problem right there, okay, divided by the standard deviation, which they tell me is 3 days. Okay, 342 minus 336 is 6. So this is 2. So if I go back to my distribution,